I will never get used to that. So, last class, we started talking about deoxy sugars. And one example we had was we just went through how to use the Burgess reagent, how we can use xanthates to do eliminations that can generate these kind of double bonds, and then how we can use those double bonds to generate, a deoxy sugar, a fully deoxy sugar. So we have two different ways to get to the double bond. There are lots of other ways. And then we can get the CH3. So we're missing an OH at C6. Now we can also get those same kind of double bonds a few other ways. So if we think about the example where we use glycals, let's say we used galactose. We would make this from a glycal. This came from a glycal. We used IDCP and then methanol, I guess in this case, is the nucleophile. Go back a few lectures. Now, if I treat that with a strong base, a reasonably hindered base, the one I use as an example a lot is, let's use a non-nucleophilic base. So potassium terpetoxide, for example. We use a nucleophilic base in this case. We have some risks because we might take off our acetates, because you remember that we use a nucleophilic base like methoxide and it removes our acetates. So let's use something non-nucleophilic. It's not going to react with the carbonyls. That's going to look for the most acidic proton in the molecule, because that's what bases do. Can anyone point me towards the most acidic proton in the molecule? I probably wouldn't do this with acetate protecting groups. I'd probably, you know what? Let's just avoid possible complex. I think it would still work, but let's just avoid possible complex answers. So put benzyl groups on there. Now I'm fine. Now I'm very happy. So where will be the most acidic proton? The most acidic hydrogen on that sugar?
The one on C6. Well, two of them.
Okay.
Is it?
I disagree with you. Those are possible. So what makes a proton acidic?
The one into C1.
Sorry, Hazel?
Easy to lose.
Easy to lose. What, okay, I completely agree with you. What makes a proton easy to lose?
When it's, what's the word? Electrophilic?
Yes, I agree with you. Yes. What makes a proton electrophilic?
When it's positive charged. It's always positive charged.
What makes a proton positively charged? So why is a hydrogen positively charged on a molecule, I guess is what I'm saying.
Lose an electron. Like
right?
The electron is pulled away from the hydrogen.
Okay, what makes the electrons get pulled away from the hydrogen? I'm trying to get to the root cause of all this.
Okay, connect to a very negative or electronegative atom.
Yes, I'll accept
Oh,
that. So they're at a stable point. What we want to do to make a proton acidic on a molecule, you need the resulting anion that's formed to be stable. That's what you need. Okay. I don't love the stability of the C6 anion because I can't delocalize, I can't do anything with that anion. Now, the one I'm thinking of isn't initially stable, but it stabilizes itself very quickly. So it's kind of a trick question. Rona has said the one on C1. I think she's close, but she's not right. And the reason she's not right is momentarily when you generate that, you are going to generate a negative charge in an sp3 orbital there. And there's not a lot of places that can go. That's not massively stable. I will agree with you, Ronaz. No, like I should be really careful what I'm drawing here. It's kind of, there's a negative, there's no, it looks like there's a carbon, there wasn't. I will agree with you, Ronaz, that the electronics on that carbon are the most favorable for the generation of a negative charge in that you have two oxygens both withdrawing by induction, which is good, is the best. I agree on that front, it is the best. But we're missing a key avenue of stability that's available to another proton on the molecule.
C2 because of the iodine.
I agree that the induction there is going to be good. I don't think it's actually as good as C1, so I don't think it's C2. You have another option. So we've done C, it's not C6, it's not C1, it's not C2. It's not the benzo groups. It's not the methyl
It's
groups.
the methoxy.
Nope, it's not the methoxy.
Ah,
5.
Nope, it's not 5.
Wait, didn't we just rule out all the options?
Nope, you still have 4 and 3.
Did you just say not iodine?
It's not 2, but you still have 4 and 3. You still have protons on carbons 4 and carbon 3.
Oh, 4 and 3. Why would one be more acidic than the other? They're the same, isn't it?
Nope.
one of them is equatorial, one of them is axial.
You have an E2 elimination from the one on carbon 3. It's antiperiplanar to the iodine, and it is adjacent to the iodine. That is a really acidic proton. That's going to come off in a flash. And it's because the negative charge that is formed by taking off that hydrogen can stabilize itself by donating, basically using the anomeric effect, by donating to the anti-bonding orbital of the carbon-iodine bond, which is very breakable. And so the negative charge on C3 is highly stabilized because it can donate into the anti-bonding carbon-iodine bond, and it donates so well into that bond that it breaks the bond and makes a new double bond. That's how all E2 eliminations work. So, but again, you need to be antiperiplanar. And again, okay, I'm just getting, there we go. Just wanted to hide my, and you get the axial attack of the hydrogens. This one was axial when it was kind of in a twist boat, which we would have had back here, but I've drawn in a chair now. So you get the hydrogens delivered from the axial side, so you generate a C2 deoxy sugar this way. You could have also gotten a C2 deoxy sugar by taking that and hitting that with a lithium aluminum hydride. and that's going to add an H minus and do direct SN2 on the iodine. So if you have a halide, and it's easy to get halides at C2 because we have all that IDCP chemistry from the glycal chemistry, we can easily install a C2 deoxy. C2 deoxys do show up in nature, so it is kind of a useful place to have a deoxy. C6 and C2 are the common ones. Now, I guess you can always put a halide in anywhere. A couple of reactions that can be useful for that are, let's say, halide introduction. We're going to see this again in the amino acid stuff, because you can actually use this to make a lot of biomaterials through kind of linker kind of chemistry. And we'll see our first example of a useful biomaterial in this section right here. So let's say we have this molecule. I'm going to modify this slightly just because I'm going to make it virucidal. Sorry. So these are really highly virucidal types of sugar mimetics that are formed by some bacteria. That bacteria then used to kill each other, because bacteria are nasty pieces of shit. It's basically a sulfuric acid attached to a sugar. And they can incorporate these into peptides. Normally they incorporate through the anomeric center into peptides on their surface, and they can make their surface really, really acidic. That can prevent viral entry. It can also really start targeting other bacteria in the environment by rapidly producing this. They can make their environment rapidly very acidic. They survive, the other bacteria don't, because bacteria are basically out there to kill other bacteria. It's nasty, brutish, and short. But let's say we want to introduce a halide onto this, because let's say we want to make a synthetic equivalent of this kind of molecule. So what's very useful is we have chemistry that can functionally interconvert any hydroxyl group selectively to a bromide or an iodide, depending on our need. And we've got a pair of reactions. One is called the Gehrig iodination, named after a guy named Gehrig, who was Swedish. There aren't a lot of reactions named after Swedes. It's kind of surprising he didn't win a Nobel Prize, because the Swedes love giving Nobel Prizes to Swedes under any excuse they can. God help you if you're not, Swedish or American or British. And the Apple reaction, and this is a bromination. So these are related chemistry. One's going to give us an iodide, like it's an iodination, which kind of gives the game away. The other one doesn't tell you that it's a bromination, and it's named after some German chemist named Apple. Both dead white dudes. Actually, Gehrig is only recently dead. The Apple reaction has been around since the 1800s, I think. The Gehrig iodination was from about the 1970s. So how these work, they both kind of work the same way. I guess, which one's easier? I think the Gehrig is easier mechanistically. So what you do is you take any alcohol, you treat that with triphenylphosphine and iodine. And normally we'll have a weak base in there somewhere too. I don't know. You can use Halide. So, and we're going to result, and the overall scheme of what we're going to get is we're going to get Ri. So what ends up happening here is the triphenylphosphine attacks the iodine. Generating triphenylphosphine iodide and iodide. Why does this happen? Well, iodine is of course is completely non-polarized bond, but it's polarizable in that at any given moment, one of the iodines can be slightly more positive than the other ones, and so the triphenylphosphine can attack that. And almost all heteroatom bonds, like bonds between atoms that are not carbons and hydrogens, are weak. Like oxygen bonds and peroxides are really weak, and that's why peroxides make good bombs, and they're also good cleaning agents. Nitrogen single bonds are really weak. Nitrogen oxygen single bonds are weak. Nitrogen halide bonds are weak. We've seen that already with using and bromo and N-iodosuccinimides to activate thioethers. ethers. So it's unsurprising that halide bonds are weak. And this is why iodines are really good disinfectant, because you can add it onto your skin and it starts reacting with all the double bonds and everything in there and can kill all the bacteria, because bacteria have double bonds in their membranes, and you start ionating those, and then everything goes to shit for the bacteria and the bacteria dies. So, but for that to happen, iodine needs to be reactive, and here it is, we're using triphenylphosphine. So we get this. And now what can happen is we're going to take advantage of the fact that oxygen just loves phosphorus so much. And so the oxygen is going to come in and displace iodine and attack the phosphorus. Notice we've got a lot of I- floating around now because we already had one. Now we've got a second one. We got this little weird situation where we got a double positive that lasts for all of 0 time. Probably because our collidine is going to come by and pick it up. Theoretically, you can use the iodine to do it, but we don't really want to make hydroiodic acid. Not fun stuff. So how I was just saying that heteroatom bonds are weak, single bonds are weak. They really are. Except oxygen really wants to make that extra bond to phosphorus. Triphenylphosphine oxide, which is triphenylphosphine with phosphorus making 2 bonds to oxygen, I think is basically like a heat sink for the universe. I'm not going to be surprised if we discover triphenylphosphine oxide floating around in the universe, like in the atmospheres of Venus or something, because I think everything will eventually become triphenylphosphine oxide. I've isolated more times than I care to think by accident. So now what happens is one of our iodines can attack that carbon, break off the oxygen, which can then make its double bond to phosphorus, and it's happy. Note the phosphorus is now neutral. And we're done. So this is a Gehrig ionization. What we've done is we've traded an oxygen for an iodine. And what's really cool about it is you can have free nitrogens, you can have free sulfurs, you can have acids, you can have esters, you can have all sorts of functional groups. and this will only react with alcohols. So it's ridiculously selective. So we can do it with this guy up here, which has a freaking sulfuric acid in it. And this molecule, this is only going to react with the alcohol. The Gehrig, the apple reaction is related. Uses CBr4 and triphenylphosphine. It doesn't use bromine, BR2. You can do this with BR2 in the same way we just saw it with the iodine. Nobody does because BR2 is scary. And the less you can use that, the better. CBr4 is a beautiful solid. It's much less reactive. It's not going to do anything else except this. Whereas BR2 can start reacting with all sorts of stuff, and you can have problems. So it's related in that, overall it's the same thing. It's just your source of bromine is a little bit different. So as Ronaz was pointing out a little bit earlier, and as Hazel was pointing out, having an acidic proton or having a reactive electrophile is all about how stable is the anion that's left behind. In this case, the anion that's left behind is CBr3. So it's a carbon attached to 3 bromines, each hauling electrons for everything they've got. It's pretty stable. But not super stable. So when it goes around, floats around, it sees an alcohol, we'll strip off the proton from an alcohol. Now we get the same chemistry we saw just earlier with the Gehrig iodination. Exactly the same thing, except now our halogen is bromide. And we generate triphenylphosphine oxide and your alkyl bromide. So all this chemistry is actually on its own. Making a bromide from an alcohol is not a favorable process. Alcohols are more stable than bromides, definitely. But we're relying on the fact that we're making triphenylphosphine oxide, which is ridiculously stable. So we're coupling an endothermic reaction, a reaction which requires energy going from OH to bromide, which is unfavorable, with a massively exothermic reaction going from triphenylphosphine to triphenylphosphine oxide. And so that oxidation of triphenylphosphine oxide is paying the price needed for the cost of going from an alcohol to a bromide. And now we can make something more reactive, a bromide. So if we go back to the example that we started with, and let's say we do a Gehrig iodination on this. I'm just going to switch up my base this time. I'm going to use imidazole instead, but whatever. We will get our iodide. Now, with an iodide there, we can do all sorts of things. We can reduce it off. So we're going to talk about that in a moment. We can treat that with lithium aluminum hydride, and we'll just get an iodine at that point. Sorry, these are protected. I think these are benzols. They were not free OHs, otherwise this would be a lot messier. We can do something we're going to see in a few minutes, which is a radical reduction. But the other thing we can do is we can make a polymer out of this, because we can take something like this guy, whose name escapes me for a moment. It's the polymer generated from ethanol. I can't remember. It's a polyglycolic acid. Anyways, treat this with the base. We deprotonate all the OHs. And we can start doing chemistry at the C6. And we start then attaching a sugar well, I guess there's a better way for me to represent that, isn't there? Start attaching a sugar at every one of these sites along there. And now we have a polymer of a rather dangerous biocide that's made up of a sugar and a sugar derived, because you get this from digestion of glucose polymer. So we have like a purely biomaterial, which is really, really highly bactericidal, which is kind of cool. So again, if you haven't seen this notation a lot, what this means is in brackets, I have repeating units. I guess this isn't quite right, actually. And I just repeat this n times, where n is it's the polymer repeat number. I'm not defining what that is. You can. It might be 10, it might be 1,000, it might be 1,000,000. And so what this is a repeat of CH2, CHO sugar. Then it's going to be another one of these CH2s and a CHO sugar, another one of those, another one of those, another one of those ad infinitum. So what we've done here is we're able to use the halide as electrophile. So we're going to come back to that concept very, very soon. The last thing I want to do before we move on from deoxy sugars, there was a little bit of a sidebar there because I wanted to talk a little bit about how to put in the halides, is let's say we have a sugar. Similar one. We've got two options here to how to turn this into, well, we have a bunch of options, how to turn this into this. So last class, we saw the Burgess reagent, which would have worked. We saw using a xanthate and heat, which would have worked. Right now, we've just seen that we can do the halide. enough palladium on carbon with hydrogen would do it too. Or what I'm going to talk about preferentially using, or, strong base. Which we saw. So we did the E2 followed by reduction with proton. What's important here is if you're ever going to do this approach using hydrogen gas and palladium on carbon on a double bond, you will always get the equatorial substituents, which is fine. I want equatorial. But if I wanted that axial, I'd be fucked. I couldn't do this. Or we can use radical chemistry, and this is what I want to talk about right now. Because it's very, very selective, very, very specific. So how does this work? This is Lenin's favorite chemistry. So what we do is we can take any halide, treat that with, we're going to walk through the mechanism of this. Just point out where this comes from. So we get the hydrogen coming from the tributyl tin. What's nice about this, so this is precisely mechanistic, not mechanistically, but functionally it's the same as treating that halide with lithium aluminum hydride. The difference being lithium aluminum hydride will rip apart most of your molecule in many cases, whereas this is very, very gentle and soft and won't touch much of anything else. Be nice if you don't have any double bonds. So AIBN I want to make sure I'm actually drawing that right, because right now I am suddenly blanking on it, and which is really weird. Is that. Okay, why is that important? So it's important because what we have is something that is 75% of the way to being nitrogen gas. And as much as I want triphenylphosphine oxide to be the heat death of the universe, nitrogen gas probably is. Once you make nitrogen gas, it's really hard to unmake nitrogen gas. Probably the most important discovery in human history was the Haber process to fix nitrogen gas into ammonia, and we can use it as fertilizer. And that means that, the world population can go from what it was in the beginning of the 20th century to all of us being alive today because we have enough nitrogen fertilizer to grow crops and we're not all dying of starvation, which is humongous. It's probably the single biggest contribution to human well-being in history. And it's unfortunate that then Haber went on, because he was a gas expert, to generate poison gases for the German military in World War I and World War II. But I guess that's the way things go, is science is neutral, except when it isn't. It's how we use it that matters. So you can save millions of lives and you can kill millions of people. Anyways, take AIBN, you heat the crap out of it. That's why I refuse to work on explosives research. I'm fascinated by doing explosives research, but the only application of new fancy explosives is to kill people in new ways. And no, thank you. We've got enough ways to kill people. Not interested. So you generate two of these radicals and nitrogen gas. Nitrogen gas, of course, is super stable. You need to use the Haber process, which basically involves heating things to thousands of degrees over a catalyst in the presence of hydrogen gas and breaking down nitrogen gas and hydrogen gas to make ammonia. So massively favorable. This is actually very easy to do. It happens at about 70 degrees Celsius. Okay, cool. We have a radical. What can that do? So again, if you remember radical chemistry, I think all of you have taken probably this stuff. This would be your activation step in your radical mechanism. We will then have an initiation step. Initiation is when we generate a radical that is involved in propagation, which is the next step. So radicals are lazier than almost every other molecule. They will always react with the most reactive bond in a system. And the most reactive bond in this entire molecule system, everything we've got in there, is the hydrogen tin bond. So note again, if you need to review radicals, not a bad idea. Wikipedia has a pretty good webpage for it. If not, any introductory chemistry textbook, organic chemistry textbook will be fine. But we're drawing single hooked arrows to represent a single electron moving. And what we've done is we've used that radical that we generated to react with the most reactive element or most reactive bond in the entire system. That's all radicals ever do, is they react with the most reactive thing in the entire system. So we have now generated a radical that we are going to see in propagation. Some people would call both these steps initiation, and that's fine. I'm a stickler apparently for this. I'm not normally much of a stickler on stuff. This one apparently I care about. I prefer to separate them, where initiation is a step that involves the generation of a radical that is present in propagation. I'm not enough of a stickler that I would take any marks off if you happen to label these wrong and it was part of an exam question. I don't think I will be asking exam questions that require this mechanism. For the most part, you'll just be allowed to use the reagents. But I hate saying, here's a reagent, I told you this is how it works, as I told you so. It's like, no, let's go through the mechanism. Okay, so this is what happens. Now we have the propagation steps. And I think this is why radical chemistry confuses people. And it confused me a lot until I realized that radicals always react with the most reactive bond present in a molecule, in a system. So we just generated this tin radical. The most reactive bond present in the system is the bond. It hasn't changed. It's the same bond. It's just when this happens, as we note, nothing productive occurs. The things on the right-hand side of the arrow are the same things as on the left-hand side of the arrow, so nothing interesting happens. But occasionally, the radical reacts with the second most reactive bond in the system because it encounters it first. And the second most reactive bond in the system is our halide. So on a few cases where the radical does not find another equivalent of tin hydride, it finds a halide first. Carbon iodine bonds are very weak. You can look up bond dissociation energies if you like. I don't want to. They are boring. Ha! We generate a new radical, which is now going to react with the most reactive bond in the system, which is still the tin hydride. because that has never changed. You know you are done propagation when you regenerate the radical you start with. Or I guess, in this case, I think I've only ever seen one example where there's more than two lines. Like we had that top line there because I'm trying to prove a point. You wouldn't normally draw that in mechanistically. I think it's important for me when I'm teaching this, it's important for me to draw it in because otherwise you get people, well, why does it do that if it's going to react to the most reactive thing? It does, it's just nothing interesting happens. So normally this is only two lines because the first line is an accident. The radical is not reacting with the most reactive thing in the system, it's reacting with the second most reactive thing in the system. And in that case, what it's going to do immediately is react to the most reactive thing in the system, which generates the radical that you began with. So you almost can't, by definition, have a propagation sequence that involves more than two steps, unless you're kind of like pushing a radical around from resonance or something weird like that. It just isn't physically possible. It's just because that's how radicals work. Then you can draw termination steps. Nobody cares about termination steps because termination steps are not where you get your products. Products are always from propagation steps. But anyways, termination steps, you combine all radicals with all other radicals, and this is why a major byproduct, the major byproduct of this chemistry is ditin hexabutyl group. This is ridiculously toxic because it is so hydrophobic. It crosses your skin immediately, and then you get tin, and it localizes to your brain, and the tin never comes out of your brain. And if you get enough of this tin in your brain, you die. So, I like to say that whenever I am particularly unorganized, it is the tin in my brain speaking, because God knows I've got enough of this in me. Just from doing years and years and years of tin chemistry and not having been taught that it was particularly dangerous and that you could easily get it into yourself. And I'm not bitter at all, but my life is probably going to be shortened because of this. So when you work with tin, halide tins, always double glove, always make sure you're doing everything inside of humid. It's very safe if you don't get it on you. Just make sure you don't get it on you. So I'm probably fine. I don't have that much tin in me, but still, I like to play it up. I think there might be varying levels of sympathy for the class. So so this is what's going on with the radicals that you happen with this, and any halide works. Brome, except fluoride. Fluorides are really stable. They're weird. Like fluorine is a halide by technically, but it's different from iodine, chlorine, and bromine. So you can use this radical chemistry for all of that. The other place where we often see that though is we use a different radical source because it's just a little bit cleaner. So again, we're going to use basically the same. You know what? I'm going to switch it up a bit just because I'm bored, basically. So I have an N-acetylamine. This is because we're going to talk about some C2 nitrogens next. And what we can do is we can make the xanthate that we talked about. So remember, we talked about this last class, or 2 classes ago, I guess, because last class was a midterm, which I haven't looked at. I probably won't mark it till early November, but I will try and get that back to everybody. If anyone, yeah. So this is actually, we can do very, very similar chemistry. The nice thing about this is the xanthates are super reactive. So whereas with the halides, you need to be very, very careful about not having other double bonds or something else in the molecule because they're not as reactive. If you do this kind of radical chemistry, the xanthates can be done in the presence of double bonds. Halides. I'll stick with the terminology double bonds. You can even do them in the presence of halides. They're just really, really selective. I don't think I'd recommend doing them in the presence of halides, but I've done it. At least in the presence of a chloride. I've never tried. I'm sure it wouldn't work with an iodine in my hands. Other people have done it, but other people are better chemists. So it's very, very similar chemically. Again, we do the AIBN stuff we've just seen. We have the tributyl tin hydride. Not going to repeat all that. So what we end up getting is the tin radical. And I need to make sure I do this right because I can easily get kind of sloppy on this. Yeah, okay. No. I'm gonna put that in brackets. No, I screwed that up. I'm trying to do something else. I'm gonna open my notes because apparently I am just blanking at this moment. There we go. So what we're relying on is the formation of a strong sulfur tin bond. And we generate a radical here that's stabilized because there's so much, so many orbitals around it, but it's not going to last forever. And we're going to go and generate a thiocarbonate. And it's so favorable to form that we can form this very unstable radical. It's a primary radical. Like it's on the C, in this case, it would be on the C6 of the sugar. I'm just not drawing the entire sugar. And of course, that's then going to react with the weakest bond in the entire system, which has remained the tri-tin butyl hydride, the hydrogen of that. And we regenerate the tri-tin butyl radical, which can then go and find another xanthate. This is a ridiculously favorable reaction. This product over here is so freaking stable. It's not even funny. And that's what allows us to generate what is considered a very, very unstable primary radical because it's through decomposition. And that radical then reacts immediately to quench itself. So this gives us a whole bunch of ways to generate deoxy sugars. I actually didn't draw in a product up there, so I'll do that now. Sorry for the small size, but just give myself a little more room. So the important thing here is that we have this CH3 installed. So we've got a bunch of ways to make these deoxy sugars. We can do reductions, we can do radical chemistry, we can do nucleophilic attack on halides, we can do, lots of options. You got lots of ways of doing this. And what's cool about this is I've drawn this on C6 because C6 is available to me. This is very easy to implement on any of the OHs. So you can always introduce that. I'm actually going to rephrase this a little bit more carefully. Deoxyamino sugars. Amino sugars gets a little tricky on exactly what we mean by that. So a deoxyamino sugar is where we replace an OH on the ring with a nitrogen. So the most common place to do this is at C2. And it's almost always in the form of an acetate. And I realized that this morning I looked over the exam and I asked the TF antigen, which has a C2 acetate acetamido group, and we haven't talked about that. So I'm going to be very, very generous with anything that I see on there, even if it's all the OHs or people magically putting nitrogen in through using something. I'm basically going to just whatever for how that what's going on with the C2 group. That was a mistake on my part. Regardless, with we want to have ways to introduce this so we can make things like the TF antigen or the TN antigen. What I've drawn here is the TN antigen. This is a blood marker that's found on, along with two of its partners, on 95% of all cancers. Be a really good target for vaccines if we had some. It's also a really good diagnostic target because it is not found on healthy tissue. So if it's present, you got cancer. And if it's not present, you almost likely don't have cancer because it's found on 95% of cancers. And it's not associated with how cancers form. So we don't actually precisely know what the hell it's doing. I think I do work on this. So my personal thoughts are that if you have these special sugars present, it helps the tumor get established and kind of bind to things and kind of form a cluster of cells so it doesn't get wiped out by the immune system. So it's not essential for the tumor becoming a tumor, but it's essential, nearly essential for the tumor to avoid getting destroyed before it gets established by your immune system. So what we're hoping to do with our vaccines is either use it to kill cancer or use it to force the cancers to abandon these kinds of molecules on their surface. And if they do, and by mutation, and if they do that, suddenly they're not able to avoid the immune system as well, and maybe your immune system can mop up. Anyways, it's personal ideas and screeds. What we need is a way to get nitrogen there, and we've got a few ways to do that. One, and I think the easiest, is from a glycal. Actually, there's a few different ways from a glycal. And Hazel knows all about one of them. So if we, again, let's say we use our IDCP and we use something like methanol, you don't really need a smiley, do you? More of like a face of eternal horror and screaming. Anyways, we can do this, and remember IDCP makes the iodine on the top face. Then the methanol is going to come in on the bottom face to this kind of pseudo-oxocarbenium that we generate to give us this guy. Okay, so we've seen this before. Never hurts to review. When we were talking about this, we were saying, well, what we can do with that iodine is we can displace it with an oxygen nucleophile. We can regenerate the glucose-galactose stereochemistry. But now we've seen what we can do with halides. There's all sorts of things we can do, right? We could reduce that off with hydrogen, like lithal, or we could reduce it off using radical chemistry, or we could reduce it off using palladium on carbon, and in all those cases, we generate the deoxy sugar. Or, excuse me, relevant for us right now is we could use sodium azide. So azide N3 is just a little weird to draw. It's got two negatively charged nitrogens. Everything's making double bonds, everything else. Positively charged nitrogen in the middle. Overall, one -1 negative charge. You can draw lots of resonance structures if you like. But they kind of generate 2-. This is definitely its happy one. And this is a really good nucleophile. I'm going to switch colors so it's a little bit clearer. A little bit upsets me that PowerPoint only has like 8 colors. I'd really like a hot pink is what I really want. Like, there's no hot pink there. I wonder if there's a way I could program PowerPoint to have different colors. I'm sure I can. Now I just need to figure out if I care enough about hot pink to spend probably a couple of hours reprogramming the source code of PowerPoint, and I don't think I do. Microsoft source code is also really hard to modify. Okay. Oh, this is Office 365, so it's all on the web. Yeah, no, I probably can't. Regardless, you can displace the iodide with an azide. That's cool. Azide's not a, we got a nitrogen, but the azide's not a NAC or an amine. And so what we can do with this is a few different things. The easiest is hydrogen on palladium. Hydrogen and palladium on carbon. I keep saying that wrong. I have a mental block. So we can introduce an NH2. Now, generally, the nitrogens in amino sugars do exist. So you do get some examples where you just have an NH2 at C2. But NH2s are very reactive. So biology tends to protect them as the acetate. And for reasons I do not understand, we need to basically use acetyl chloride and something like triethylamine to add the acetate group. You can't use acetic anhydride, it doesn't work. It's not electrophilic enough. It completely should be, but it isn't, and I don't know why. I'm sure somebody does. It's just, I guess I've never cared enough. I'd accept it though for this course if you use acetic anhydride or sodium acetate acetic anhydride. Good enough. That's what we're using with the OHs to put on acetates. I'll accept it for the nitrogen, but it wouldn't work. You need to use acetyl chloride. That's one thing we can do. Another option we have if you don't want to use hydrogen on palladium on carbon, because in this case we have benzyl ethers, and the benzyl ethers might start coming off under these conditions, because this is how you remove benzyl ethers. Normally you need a bit of pressure. So if you actually did this at like ambient pressure just with a hydrogen balloon, you probably would not take off the benzyl ethers. You normally need a bomb reactor to do that. Except in the case where you don't want them to come off, in which case they probably come off great under a balloon. Because fuck you, that's why. Another option is you can use, oh look, it's triphenylphosphine again. And this can be used for something called the Staudinger reduction. And I'm going to leave this as an exercise for you guys to look at the mechanism of a Staudinger reduction. And I'll write it out really clearly so you can easily Google it. That'll also get you to the amine, and then you can treat that into the N-acetyl group. There are lots of other ways and things you can do, but let's stick with two. I think that'll work for everything. Again, this is very selective. It's not going to touch anything else in your molecule. It's probably generally preferred for doing any kind of chemistry like this. I have never ever gotten one to work, but everybody else gets them to work. It's just, I personally, this is my kryptonite. I cannot get this reaction to work to save my life. But no one else seems to have any trouble, so I don't know what the hell I'm doing wrong. Doesn't matter. It works on paper and it works in reality for anyone who's not me. So these are, what we're doing here is this is kind of direct displacement. approaches to introducing nitrogen. So another way to introduce nitrogen, and this is the one that Hazel loves, is to use, I don't even know how to define it. I guess it's Lewis acid. Mediated. It's nice because we don't need to make the halide. Nothing else about it is nice though. So let's say we have a glycal. We treat this with ceric ammonium nitrate and sodium azide. So cerium, bunch of ammoniums, and a bunch of nitrates. I get very uncomfortable with how many bonds that cerium could be making in this situation. Making all the bonds to the nitrates, and the ammoniums are hanging out very close to it. And I do not like this at all. Essentially, what we have is cerium 4 plus associating with the double bond as a Lewis acid. And now normally when you would have any kind of positive thing here with the, we saw this with the iodine, we saw this with the with everything else. If we had anything kind of associated with the double bond, our nucleophiles came in here at the C1 position, and we snapped that open, like with epoxides or iodines or anything like that. Cerium's weird. And instead what happens is we get attack at this nitrogen, at this carbon. There are some nitrates on here still, for sure. I'll just draw one in. Nitrate, not nitrite. And so we get azide at the down position. And then we have cerium and I'm saying Ln on the cerium because I'm not saying how many other ligands are there. I don't know. I'd be lying if I drew anything defined. And I think at this point, the cerium is normally about 2 plus, but it could be 3 plus. It's anywhere between 2 plus and 4 plus. Doesn't really matter. The cerium's a complicated mess. But what we end up doing either way is swapping the nitro group for the cerium. So we basically have a reverse insertion. So often we see insertion of atoms into bonds, and here we're seeing expulsion of the atom from the bond. So we're expelling the cerium. And we have a nitro group like that. Nitro groups are great leaving groups. That is not going to stay static for long. So often what ends up happening here is you treat this with almost any nucleophile, water, thiophenol, chloride, it doesn't really matter. Because this guy, now of course you need to do the twist boat, right? You can't kick out a beta group, it needs a twist boat, so it's the axial, and so you can expel, is constantly in equilibrium with the oxocarbenium. So it doesn't take much for a nucleophile to come in and attack. And it's normally from the alpha phase. Often we use chloride because then we can displace, or you'll see people using water. I just, for no reason I can think of, chose to use thiophenol here. But normally there's some water in there, and eventually you're going to displace it and you can hydrolyze that bond. And what we've done there is we managed to insert the azide, again, which we can reduce using all the same techniques we talked about, down to the amine. We managed to insert it directly on the glycal using a single reagent, the cerium ammonium nitrate. But again, we have a glucose-like stereochemistry here. There's no real way around that. You can't make the mannose-like one that way. So let's say we want to make the mannose-like one. What we would need to do to make a realistic molecule here is we would need to generate the C2OH. Everything else protected. We then oxidize this. Recommend maybe the Sworn oxidation. And we take this up to the ketone. Now, theoretically, anytime you have an sp2 center, you can't draw a chair, so I'm going to draw this as a boat. And then what we do with that, once we have that, is we can treat that with an amine to make an imine. So what we're often looking for in the form of an amine is something that we can turn into nitrogen really easily. I'm trying to think of what a good one is. So common one you see for this is this guy. So it's benzylamine, the paramethoxy. Why the paramethoxy? Because we can use the DDQ reagent to remove that, as we saw when we talked about paramethoxy benzyl groups back when we talked about protecting groups. So if we treat this with a little bit of acid, we can generate the imine. Okay. Why does this help? Why does this get us anywhere? What the hell does this mean? Well, from here, what I can do is I can reduce. I can use a very weak reducing agent, sodium cyanoborohydride. If you haven't seen this guy before, all it does is reduce imines to amines. So it reduces double bond nitrogens to single bond nitrogens. And again, like all these other things we've seen, it prefers axial attacks. Well, it prefers to actually attack from the bottom face. Because shit, no, prefers axial attacks. That's not going to help us get the glucose or the. Yeah, we're fucked to get mannose, aren't we? To get the mannose, I think we need to do direct displacement of an iodine as equatorial. I blanked. It's going to give us the hydrogen from the top face, of course, because that's axial. So I'm going to have a very quick bar at the end of this to how to get the mannose thing. Everything else is intact. And then we can use DDQ to cleave off this and provide us with our amine. So if I wanted the mannose-amine, so this is imine ketone. Okay. So what we've done is we've oxidized up the OH to a ketone. We've transferred the ketone to an imine. We reduced the imine to an amine. And then we hydrolyze off the protecting group to give us the free amine. It doesn't work great with ammonium. You almost need an R group. It would be really nice if you just use ammonia, because then you wouldn't need to do this whole cleavage of stuff. It's just ammonia imines are not very stable. They just don't really form nicely. So you're kind of screwed. So you do need something like this. It's irritating. So how to get mannose? Essentially what we need to do is, let's say we made this guy. We would need to do a displacement with a nucleophile. The rest of it's like sugar, I don't care. And then another displacement with another nucleophile, so double inversion. You could also do this using Mitsunobu chemistry from the alcohol. So another thing you could do. I'll leave this as an exercise. There's probably better nitrogen sources, but I'm just not seeing them right now off the top of my head. So you can look up Mitsunobus with nitrogen. And this would be the way to introduce. That mannose type stereochemistry at C2. There's not a lot of C2 mannosamides. I can't think of any, but I'm sure they exist and they'd be useful if they don't. So, or any kind of other axial nitrogen that you want. So we've seen 3 core ways to introduce nitrogen. We can either do direct displacement with azide, we can use the steric ammonium nitrate approach, or we can do this imine, ketone to amine approach. All of those, with the exception of direct displacement, will give us the glucose galactose, like the glucose form of a nitrogen. It'll give us an equatorial nitrogen. Why? Because the equatorial nitrogen is more stable. And hydrogen attack is always from the axial phase, and that's what they all rely on. If you want a Amino style nitrogen, you need to play around with the direct displacement. You can do that either through however many inversions you need to introduce a nucleophile through SN2s, or you can try using Mitsunobu's directly from alcohols. I'm going to leave it there. We're at 9:54. I'll post the slides. Again, I'm hoping to get to, I'm probably going to mark the midterms next week. So you should get them back a week Monday. Okay. Any questions?
I have a stupid question. And in apple reaction,
Yeah.
is it okay to use for example, CI4 instead of?
Yeah, you'd think so. I think I've seen that once. It doesn't seem to work as well. So you can.
Oh,
I think the iodine is just so cheap, so I think that's why we see so much of that. My God, we covered a lot of stuff today. Like there's nothing, I think you can use CI4. I've never done it, but I don't see why not.
thank you.
Yeah. It doesn't work on carbon tetrachloride. You can't use CCl4.
Oh,
It's just the chloride's not electrophilic enough, but the iodide should be, and I think the CI3 should be stable enough that you can actually do it. Like, bro, this is kind of like perfect. It's the perfect balance of the electrophilic halogen, like the bromine being big enough to be electrophilic, and the CBr and the bromines that are left being good enough at stabilizing a negative charge. I'm not 100% sure that CI3 can stabilize a negative charge. I think it should, but I don't know.
okay,
Okay.
thank you.
Yeah. Just use iodine. Just use the Garrick if you want to put an iodine in. Okay. Thanks everyone. I will leave this here.